SwayamPrabha. Digital India. Educated India.
We will continue our discussions on particle impact, which we started in the previous lecture. We are going to look at some problems and the application of the theory that we have developed. To reiterate, impact is a short time impulsive interaction between two particles, and we have discussed or classified impact in three forms: elastic impact, inelastic impact and plastic impact, which is merger. And we have used this fact that short time change in the linear or angular momentum of the system is 0. This is for a very short time for which that contact is present, the impacting situation is present. And all through our discussion has been for frictionless interaction or frictionless impact. Let us look at a problem. This is from the book of Merriam and Craig. Sphere A, which is this blue sphere, collides with sphere B as shown in the figure. If the coefficient of restitution is 0.5, determine the x and y components of the velocity of each sphere immediately after impact. Motion is confined to the x y plane. As you can see in this figure, the incoming velocities are specified. These are marked as V A and V B. We have been using u as the incoming velocity and v as the outgoing velocity. So, that is specified. You have to find out the components of velocity along the x and y for each particle. The masses of the two particles are specified. The angle at which, with respect to this x y frame, the angle at which the impact is taking place and the incoming velocities are all specified. First, I choose this coordinate system which we had been using. We have developed our discussion using that normal and tangential vectors. Since this problem has been specified to be in the xy plane, therefore, our discussions that will suffice, our developments that we have discussed in the previous lecture, that will suffice. Therefore, we have this n cap, which is the normal component of normal vector, unit normal vector, and t cap is the tangential vector. So, it is perpendicular to the normal vector, unit normal, and whole thing is in the xy plane. Okay. Now, I can write V A prime. Now, I indicate this velocity of A after impact as V A prime. So, V A prime I can write in our coordinate system that we have chosen using n cap and t cap. I am going to express everything. V A tangential prime t cap plus V A normal prime n cap. Similarly, the outgoing velocity of particle B is V B prime. This vector is equal to, again represented in the tangent normal using the tangent normal unit vectors, V B tangential prime t cap plus V B normal prime n cap. Now, momentum conservation along the tangent and the normal direction. Along the tangent direction first, because that is the simplest. The incoming velocity, and as you know that in the tangential direction, the incoming and outgoing tangential components of the velocity of individual particles, they are equal. Therefore, basically momentum before and after are equal, and that leads us to the conclusion that the velocities the tangential velocity components are equal. Here I have written the momentum conservation. Mass of particle A times the incoming velocity V A sin 45 gives me the tangential component. You see, this is V A, the tangential component is this, which is V A cos 45, this is 45 degree. Therefore, this is V A cos 45 degree. This is the tangential component of the incoming velocity of A, and mass times that component is the linear momentum in the incoming linear momentum in the tangential direction of body A, of particle A, and that must be equal to the outgoing tangential linear momentum of particle A, m A v A t prime. From here we can easily solve, this is trivially solved. We know the outgoing tangential component of particle A. Similarly, for particle B, in the tangential direction, the incoming linear momentum of particle B in the tangential direction is mass of B times velocity, incoming velocity in the tangential direction. Now, this angle is 30 degree. Therefore, and you can check that this is in the negative tangential direction. Therefore, I have written out that with the proper sign. So, minus m b v b sin 30 degree, sorry, this is 30 degree, sorry, this angle is 30 degree. That angle is 60 degree, this angle is specified as 30 degree. This angle is 30 degree. Therefore, m b v b sin 30 degree in the negative t cap direction must be equal to m b v b in the tangential direction outgoing. So, whatever be the outgoing velocity, its tangential component I have taken and multiplied it with the mass of particle B, that gives me the outgoing tangential linear momentum component, and that must be equal to the incoming linear momentum component in the tangential direction. And from here V B tangential outgoing tangential velocity of particle B turns out to be minus 6 meter per second. Therefore, it will maintain its velocity in the negative t cap direction. So, I have taken care of the sign, you should note this. Now, we come to the normal component. This equation we had discussed and derived, mass of particle A times its normal component. How I can find out the normal component of the velocity? Because right now this first term is the linear momentum of particle A in the normal direction, and if you look at the figure, this is V A, this is 45, therefore, V A cosine 45 and that is in the positive n cap direction, this multiplied by mass of particle A, that is the incoming linear momentum of particle A in the normal direction, plus the incoming linear momentum of particle B in the normal direction. Particle B's velocity is this. This angle is 30 degree. Therefore, its velocity is minus V b cos 30 degree n cap, and that is multiplied by its velocity. So, V b and it is multiplied by its mass, that gives me the incoming linear momentum in the normal direction of particle B, and m b times V b. So, this was V b cos 30 degree with a negative sign, and V b is 12, cos 30 degree is root 3 by 2. So, this gives me minus 6 root 3 meter per second is the velocity, incoming velocity in the normal direction. And on the right hand side, I have the linear momentum of the system after the impact, which consists of this linear momentum of particle A in the normal direction. V a n prime is the outgoing normal velocity, and V b n prime is the outgoing normal velocity of particle B. Now, we have, so once you plug in all these values, so you will get this condition. Unknowns are V a n prime and V b n prime. Now, this is our first equation that is derived from the linear momentum conservation in the normal direction. Next is this impact, remember, is inelastic. So, energy is not conserved. In the place of that, as the additional condition which we require for solution, we have been given the coefficient of restitution. Now, for normal impact along n cap, let us see what is the expression of the restitution, the coefficient of restitution. What does it say? Coefficient of restitution is nothing but the relative velocity of separation by relative velocity of approach. Now, how we can express or write this in terms of these velocity vector condition velocity vectors, so that we come up with this coefficient of restitution to be positive. Remember, coefficient of restitution is a positive scalar quantity. Now, to do that, the numerator, what I have done is V b prime minus V a prime. What is V b prime? It is the outgoing velocity of body B after the impact, and V a prime is the outgoing velocity of body A after the impact. Difference between these two is nothing but, therefore, the numerator, this is nothing but V outgoing B relative to A. V B relative to A outgoing or after impact, prime indicates after impact. V B relative to A prime means the relative velocity of B as seen by A after the impact. How will it look? Here B relative to A means you as an observer, you are sitting on A, and looking at B. After impact, what will you observe? Just think about it, you are sitting on particle A and observing particle B. What will you observe? You will observe, because it is after impact, you will observe B moving away from you, and I have taken the normal dot product with the normal. See, I have taken a dot product with the unit normal. Now, B moving away from you and its normal component will definitely be positive, because it is moving away in the normal direction, the positive normal direction. You will find that body B is moving in the positive normal direction if you sit on A. The denominator, so this is a positive point, numerator is positive, denominator. In the denominator I have written V A minus V B. So, denominator is V A relative to B. This is the incoming relative velocity before the before the impact of the two particles, relative velocity before the impact. What is V A relative to B? It is the velocity as seen by an observer on B who is observing A. Now, the situation has changed. Now, I am saying that the observer is on B, on particle B, is fixed to B and observing A, and this situation is before the impact. So, it is about to impact. So, what will you observe? As an observer, if you think about it, that you are sitting on B and observing A is coming towards you, and I have taken this dot n cap, which means this is that component along n cap. What will you observe? That along n it must be approaching you. Therefore, that relative velocity must have a positive component with the normal. Therefore, both numerator and denominator, they are positive quantities, therefore, the ratio is positive, and therefore, the whole thing works out. Now, this has to be done carefully. If there is a problem with the sign, then you will end up getting wrong results. So, please be careful about this discussion. And from here I get the second equation, which is a relation between B velocity B normal after impact and velocity of A in the normal direction after impact. So, V B n prime minus V A n prime is whatever you have on the right hand side. Now, these two equations are simultaneous equations, they can be solved together straightforward and you can get these answers. So, V B n prime is 5.25 meter per second, V A n prime is minus 1.007 meter per second. Straightforward calculation, simultaneous equation solution. Okay. Therefore, we have finally these two vectors after impact, the velocity, outgoing velocity of A and B after impact. But the question was finding out the components of these velocities in the x and y direction. How do we do that? I represent the V A prime in terms of I cap and j cap now. Now, this is the same vector, particle A has certain velocity, it has a certain velocity, it can be represented in different frames in different ways. In the tangent normal, I have represented it, I have solved it, but now I have to go to a representation in x y. Therefore, I write V A x prime and V A y prime as components in the I cap and j cap directions. Similarly, V B x prime and V B y prime in the I and j cap directions for particle B. Now, what I do is I take dot product of both this representation. So, suppose I want to find out V A, I want to find out this. If I just take a dot product of this with I cap, then I exactly filter out V A x prime, because I cap dot j cap is 0. So, I have taken a dot product with I cap, then I filter out V A x prime. I do this of course dot product on the other side also, then what do I get? So, it is V A prime dot I cap dot V A prime. Let us see what we end up with. I can write this T cap dot I cap from geometry easily. What is T cap dot I cap? It is nothing but the cosine of the angle between T and x axis. Let me call it phi. Then the dot product of T cap and I cap is nothing but, because both are unit vectors, remember both are unit vectors. So, magnitude of T into magnitude of I, both are 1 into cosine of the angle between the two, and if you do this calculation it turns out to be 110 degree. Therefore, T dot I cap is cos 110 and this n cap dot I cap is the angle between n cap and I cap. So, this angle, this is 20 degree. So, that is cos 20 degree, that is what we have here. Therefore, this must be this whatever you calculate from here must be V A x prime, and that turns out to be minus 1.67 meter per second. Same thing you can do for the j component, straightforward extension of this idea, and you can calculate everything. So, this I will leave to you to complete. Next we come to this problem. This is taken from the book of Merriam and Craig. The 2 kg sphere is projected horizontally with a velocity of 10 meter per second against the 10 kilogram carriage, which is backed up by the spring with stiffness of 1600 Newton per meter. The carriage is initially at rest with spring uncompressed. If the coefficient of restitution is 0.6, calculate the rebound velocity V prime and rebound angle theta, all are shown. Rebound velocity is V prime shown here, rebound angle theta is shown here, and the maximum travel delta of the carriage after impact, because when the ball comes and hits the carriage will take a recoil and move back. Now, here one of the particles, which is this 10 kilogram carriage, is connected to a spring. Therefore, this particle, treated as a particle, has some potential interaction, but then you remember that the impact process is such a short time duration process within which that spring will hardly contribute to change in momentum. Therefore, that can completely be dropped. In momentum change, in energy variation as well during impact, but just after impact, once this deformation starts, then obviously that spring will take in potential energy. We will use that also. First, I set up the coordinate system. Now, here because of the complexity of the motion, I have to use two kinds of coordinate system. One is for the motion of the carriage and the initial motion of the ball, etc., which is I cap. The second is because we are studying impact in this tangent normal system. So, we have this T cap and N cap. Now, this initial velocity of the ball is 10 I cap meter per second. This is the representation of the incoming velocity, which I can also represent in the tangent normal system, which is the magnitude, which is 10 meter per second times the unit vector I cap, now represented in N cap and T cap, and it turns out, which you can very easily check, as minus cosine 30 degree N cap plus sine 30 degree T cap. I have represented the incoming velocity in both the coordinate systems. Now, the outgoing velocity V prime vector. Now, this V prime vector has this, I can write it in normal tangent normal system, V prime n, which is the normal component, into N cap, plus V prime t, the tangential component, into T cap. And this impact is taking place in this plane, in the plane of our screen. Initial velocity of the carriage, which I indicate by the capital V, is 0. After impact, so V, capital V is before impact, and V prime, which is the velocity after impact, is magnitude, which is V prime times I cap. It will take velocity only in the I cap direction, and this again I represent in the tangent normal system. Why this is required? Because remember, we have been representing our linear momentum conservation in the normal direction, and there I will require the linear momentum of the carriage in the normal direction. Therefore, I have represented in tangent normal and the I cap direction. Now, momentum conservation along T cap and I cap. Along T cap, as you know that again this contact is frictionless, which you have been assuming throughout. Therefore, in this tangential direction, mv is the incoming linear momentum of the ball, small m times v vector is the incoming linear momentum of the ball, dot t is along the tangential direction, must be equal to m v prime dot t cap. The change of linear momentum along the tangential direction must be 0. So, incoming linear momentum must be equal to the outgoing linear momentum in the tangential direction, and from here trivially you can solve v t prime as 5 meter per second. Let us look at this linear momentum conservation along the I cap direction. Now, our linear momentum equation that we can write very easily. M v. Now, you can think about this thing. Let me first tell you something about the condition under which this carriage is sitting. This carriage, as you can see, that it has got these wheels. Therefore, once this ball comes and hits, it will have an impulsive reaction force from the ground as well. It will have impulsive reaction force from the ground. Now, because there is an impulsive reaction force from the ground, and because all these rollers are frictionless, etc., it is going to be only normal from here. Let us say from this part there will be an impulsive normal reaction from the ground. Now, what happens due to this is, along the normal direction, this will produce an impulsive force. Now, that is going to disturb our balance of momentum in the normal direction, but in the I cap direction, this normal impulsive force will not have any contribution. Now, remember, this normal reaction coming from the ground is because when the ball hits, there is an impulsive force perpendicular to the surface, and that will generate a reaction from the ground, which will be impulsive in nature. Therefore, if you want to conserve linear momentum, it is going to be only in the I cap direction, and so for the whole system in the I cap direction, and for the ball only in the tangential direction. Now, this I cap dot n I, the impulsive ground reaction, is 0. Therefore, that does not figure out in this the impulse because of this impulsive force. So, integral over time over this short duration, because that is an impulsive force. If you really want to take that normal reaction, now because that normal reaction is an impulsive force, even for short duration it is going to make a contribution, but in the I cap direction it does not affect. Therefore, we have taken this I cap component of the linear momentum conservation. Okay. And from here I will get this condition, which involves V n prime, V t prime and capital V prime. of which V t prime is already determined 5 meter per second. Therefore, I have my first equation from the linear momentum conservation in I cap direction. For the ball, the linear momentum conservation in the tangential direction has yielded me the tangential component of the velocity v. So, V t prime, and linear momentum balance in the horizontal direction I cap direction has given me this equation. Now, the second thing that is specified is the coefficient of restitution, again following the same points of discussion that we had for the previous problem. I have written out the coefficient of restitution using the velocities and the normal vector, and coefficient of restitution is given as 0.6. From here we will have the second equation or second condition between V n prime and capital V prime, and these two are simultaneous equations. So, this is one equation, this is our first equation and this is our second equation, which have to be solved simultaneously, and once you do that you get V prime and V n prime. This should be V n prime. Therefore, we have obtained V prime vector in normal and tangential directions, and the magnitude you can find out V prime 6.04 meter per second. Now comes the second part of the problem, which is finding out the compression of the spring. You can see that this cosine theta, we have to find out this angle as well. Cosine theta is nothing but minus I cap dot, this is the unit vector in this direction, unit vector in this direction. V vector prime, V prime vector by magnitude of V prime vector is unit vector. So, V prime cap and dot minus I cap, this is I cap direction. So, minus I cap will be in the opposite direction. If you take, these are both unit vectors, and if you take dot product of these two unit vectors, you get cos of the angle between them, and if you do that, that turns out to be, so after final solution it turns out to be 85.9 degree. This straightforward algebraic calculation and finding out cosine inverse, which you can do. Now, the velocity of the carriage after impact in vector form is 2.087 I cap meter per second. Now, once the impact has taken place, the carriage is moving frictionlessly with the spring. I can do a energy balance and find out the deflection of the spring. The kinetic energy, initial kinetic energy, spring is undeformed. So, no potential energy, half m V prime square is the total mechanical energy of the system when it starts moving just after the impact, and when it comes to a stop, when the spring has taken deformation and now it has made the carriage stop, it is only potential energy of the spring, the carriage has come to a halt, it is going to reverse of course the direction. We have to find out the maximum deflection. So, at this point is the maximum deflection of the spring, half k delta square, and from here you can calculate delta as 0.165 meter. So, the spring is going to deform this much, and of course, after this again the spring will relax and the carriage is going to move to the left. So, that completes the solution of this problem. So, I will leave you with a summary and I will close this lecture here.